All right, let's start by reviewing the basic setup of definite integrals. Again, you're given a continuous function, f of t or f of x. For our applications, we've mostly been focusing on f of t, right? The function represents the speed or the velocity. Last Friday, I used x anyway, but for variety, I will go ahead and use t today. It doesn't matter. The variable name doesn't matter, though it is suggestive of how you're thinking about it for applications. It's on some interval from a to b. So t goes from a to b. We're assuming it's continuous on that entire interval. Actually, this continuity assumption can be relaxed. You can do this kind of thing, what we're doing here, for some discontinuous functions, as long as they're not too wildly discontinuous. Like if they got finitely many jump discontinuities, that's okay. By jump discontinuity, I mean where the function jumps from one value to another effectively at one point. No vertical asymptotes, avoid vertical asymptotes. Though in some situations, even with vertical asymptotes, we can still make some sense of this, but not now. And we've got a value of n, which is going to represent the number of subintervals of the big interval. You're going to partition that big interval into a bunch of little pieces. Partition means break it up. A bunch of little subintervals of the same length, delta x, and is some fixed positive integer like 1 or 2 or 3 or 4 or 5, etc. This is an integer. Positive integer, in fact. We can, based on this, find, first of all, the value of delta x to be b minus a over n. Maybe find is the wrong word. Let me say define. Define or define delta x to be b minus a over n. What is that? That's going to be the width or length of each subinterval, which will be the width or base, you might say, of each rectangle, of each approximating rectangle. Our main goal is to find the area under the curve if the curve is above the axis. If the curve is below the axis, you actually want to find the area above the curve. Though you find it as a negative area, a signed area, S-I-G-N-E-D, S-I-G-N-E-D, signed plus or minus. Areas under the curve when it's above the axis correspond positively to the integral. Areas above the curve when it's below the axis correspond negatively to the integral. If it goes both above and below the axis, then the area under the curve when it's above, you take that and you subtract the area below the above the curve when the curve is below the axis. In a picture, if it goes both above and below like this, and we think of these areas that I'm about to shade as being positive quantities, that's A1, this is A2, and this is A3. The integral from a to b, we want to define in such a way that it equals a1 minus a2 plus a3. If I think of those a's as being positive numbers, then I want the answer to be a1 minus a2 plus a3. A2 contributes to the integral in a negative way if I think of it as a positive number. I'm subtracting it. Kind of funny to say that's what I want the integral to equal, but that is true. I want to define the integral in such a way that that will happen. Historically, Newton and Leibniz, when they were thinking about integrals, they were thinking about areas. Newton and Leibniz lived 300 to 350 years ago, late 1600s, early 1700s. Newton and Leibniz, guess what? They didn't know about limits. Maybe they had a little intuition about limits, but they didn't have the rigorous stuff that we do, even though they invented calculus. Kind of weird, huh? The rigorous stuff with limits didn't come around until like 150 years later, early to mid 1800s. Who decided to introduce limits? Well, people by the name of, should know these names. Cauchy, you spell it like that. Don't say Cauchy. Cauchy. We don't completely anglicize these names. This one either. Don't say Weierstrass, say Weierstrass. It's German. W sounds like a V. Cauchy, Weierstrass, Riemann. That's German as well. Cauchy, I believe, is French. Those three people in the 1800s, about 170 to 200 years ago, they essentially defined what limits are, and they defined calculus in terms of limits, and they proved things more rigorously than Newton and Leibniz did. Now, it's not that what Newton and Leibniz did was completely wrong. They got right answers, but they approached it from a more intuitive approach. They didn't think about Riemann sums because Riemann wasn't even alive yet. They didn't think about approximating integrals with summations and limits because, well, they were thinking in terms of simple examples, and they were thinking in literally in terms of areas. They define the integrals in terms of areas. We're saying we want the integrals to be related to areas, but we need to approach it a bit more rigorously and think about limits. So again, you define delta x to be b minus a over n. You also define x sub I to be, oh, I'm using x again now. Okay, I'll go back to t. Delta t to be b minus a over n, and t sub I to be a plus I times delta t, which, yes, can be written as a plus I times b minus a over n. Then you have, remember what we did last Friday, we're trying to approximate the area under the curve with rectangles. You have a left-hand sum, left-hand Riemann sum, and a right-hand sum, right-hand Riemann sum. They're both written in summation notation. With the left-hand sum, you use the left-hand endpoint of each interval to plug into the function to determine the height of the approximating rectangle. And if that rectangle is below the axis, if the function value is negative, then it's really going to be a negative area, so to speak. Or at least I'm going to think of the area as being subtracted instead of added, is another way to think of it. But it's still written with the summation notation. I goes from 0 to n minus 1, f of ti times delta t. Last Friday, we used f of xi times delta x, but again, it doesn't matter. I'm trying to emphasize that by using both kinds of notation. And the right-hand sum's the same, except I starts at 1 and goes up to n. In both cases, the delta t really could be factored out, and you really could just do the multiplication once. Here you could add up the f of t values, starting with f of t0, then f of t1, and ending with f of t n minus 1, and then multiply by delta t. So I factored the delta t out of each thing that was being added here. I didn't do that last Friday, but it certainly can be done. And I can do the same thing with the right-hand sum, but there is a difference. You start at f of t1. It's good to remind yourself initially here that it really is a bunch of multiplications being added up. Each of those things that I just underlined there represents the area of a rectangle. The f values are the heights, the delta t values are the widths, the bases. They're all the same base. Actually, in the more general theory, which we don't do, you can allow for rectangles that have different widths, different bases, and different delta t's. You could allow for that. it's kind of more trouble than it's worth, perhaps. But if you want a really strong, rigorous theory, that actually in the abstract is the best thing to do. You want the value of the integral to be robust, to get the right answer no matter how you approach it effectively. Is the idea there. Okay. And then neither of these equals the integral. You have to take a limit of them to get the integral. The integral, the definite integral of the function from a to b. Last Friday we wrote f of x dx. Today we're writing f of t dt, is the limit as n goes to infinity of either the left-hand sum or the right-hand sum. Now the left-hand sum and the right-hand sum are different. They do give you different values in general, but as you let n go to infinity, they should have the same limit. So you can write the limit either in this way, as the limit of left-hand sums, or this way, as a limit of right-hand sums. It doesn't matter. It should be the same answer in the end. Sometimes these limits are too difficult to calculate. Oftentimes they're too difficult to calculate. So we either try using the summations just to approximate the integrals, which is what you've done so far for your homework, and what you'll continue to do for the homework due Wednesday, maybe a little bit with the fundamental theorem of calculus, or you use the fundamental theorem of calculus. Actually, mostly after today, we use the fundamental theorem of calculus. But sometimes you can't, even though the fundamental theorem of calculus is very fundamental, and it's very true, it is the reason we have calculus in the first place, it's not always helpful. Not as helpful as you might want. You still sometimes have to approximate integrals. We'll talk about why sometimes the fundamental theorem is not helpful. When you're doing approximations, you also could average the left and right-hand sums. I hinted at that. And I think there might have been at least one homework problem where you did that. If you average the left and right-hand sums, that's called a trapezoid sum. Trap is left plus right divided by 2. Or I guess with the other notation, LHS plus RHS divided by 2. LHS stands for left-hand sum, RHS stands for right-hand sum. Could just say left sum and right sum for short. All right, let's apply these ideas to an example. Now let's see how far in this example we can get without technology. See how far we can get, okay? Let's imagine, and once again, it's a physics example, where our function is giving us the velocity. V is f of t, is let's make it 2t minus t squared. And let's use this. Let's think about this for the interval t going from, say, 0 to 5. What's going on here? What does the graph of this look like? It's always good to think about graphs when you're doing these problems, even if the problem doesn't ask for it. To think geometrically about what things mean. Remember I said earlier in the semester, it's almost always a good idea not to rush through your homework and just put it away as fast as you can. But even when you feel like the homework's not too hard, when you finish each problem, to spend at least 30 seconds thinking about whether your answer makes sense. Maybe draw pictures. In this case, draw the graph of this function. And we can think about this graph without calculus. We can, for example, see it's got horizontal intercepts at 0 and 2. It is a quadratic with a negative t squared coefficient. It's going to be an upside down parabola with intercepts again at 0 and 2. It's got to look something like this. And in fact, if you differentiated it, yes, you'd be finding acceleration, but you'd also be figuring out where the velocity is maximized. If you differentiate this, you'd get 2 minus 2t. That would be the acceleration. It's not a constant acceleration. 2 minus 2t, which is 0 when t is 2. Or when t is 1, excuse me. 1 is where the maximum value of the velocity is. I'm going out to t equals 5. And what's my goal? My goal is to try to integrate this to find what? What do you find when you integrate the velocity? Is it distance traveled? Not in general. Not if your velocity goes both positive and negative. It's not distance traveled, it's displacement, change in position. And you can see it looks like it's this area when the graph is below the axis is bigger than this area when it's above the axis. Probably we're going to get a negative value for the integral, meaning the change in position is negative, meaning if you think of rightward motion as positive and leftward motion as negative, that the bug is going to end to the left of where it started. It's moving back and forth, going to the right first, then turns around at t equals 2 and goes back to the left, and probably ends up further to the left of where it started, if rightward's positive and leftward's negative. A is 0, B is 5. Let's find these quantities like, well, delta t is b minus a over n. That's 5 minus 0 over n. That's 5 over n. We did this a little bit last Friday. Different example here. T sub I is a plus I times delta t. That's 0 plus I times 5 over n. I think maybe our delta t was is the same as before. I think these are the same, coming out the same as before. What's different is our function is different. I think we just did this with t squared before, or x squared. It was last Friday. All right, let's write down and see if we can simplify, for example, a right-hand Riemann sum. It really is a function of n. I could write RHS of n. It really is going to depend on what n is. Right? I'm not saying what n is. Now, of course, I could give you a problem and I could specify what n is. Use n equals 4 or something and you could do it. But we're trying to figure out what the exact integral is. We're going to do a limit in the end. So we better figure out what this is for an arbitrary value of n. I have put problems like this on exams before, though they're hard enough that I usually give some help. I usually make it a fill in the blank problem. You have to give reasons for things. Like, what's the reason for this equation here? The reason is this is what a right-hand sum is. Notice I'm not doing any limits yet. I'm going to do the limit at the end. This next step, I'm just using the formula for f and also the formula for ti, 5i over n. So I'm looking right here and right here and combining those. Replace t with 5i over n, get 2 times 5i over n minus 5i over n squared. That's f of ti times delta t. Delta t is 5 over n. That's going right there. I'd like to simplify this and then take a limit of it as n goes to infinity. It looks really hard. And it is hard, but it's doable if you know what to do. One thing we can do is distribute the 5 over n through the parentheses. So that's just algebra. If I multiply this one by 5 over n, 2 times 5 is 10 times another 5 is 50. I got a 50 times I over, I've got 2 factors of n in the bottom. I've got an n squared in the bottom. Here I have to square this thing before multiplying by 5i over n. 5i over n squared is 25i squared over n squared. If I multiply that by 5 over n, that gives me 125i squared over n cubed. Doesn't seem like it's helped much, but it is a worthwhile step to do. There's a couple different things you could try here. You could try subtracting these fractions by getting a common denominator, but I think a better thing to do is to use a property of summations. The summation of a difference like this can be found by doing the summation of the first thing minus the summation of the second thing. I'm breaking this apart into pieces. Why can I do that? Well, I'm not going to prove it. But effectively, if you've got something in general like this, the summation I goes from 1 to n of, say, ai plus bi, that means a1 plus b1 plus a2 plus b2, etc. The last one is an plus bn. And then because of the commutative property of addition, I can rearrange all those a's and b's. I can put all the a's together and all the b's together. I can write this as a1 plus a2, etc. through an plus b1 plus b2, etc. through bn. That's just commutative property of addition, for the example, the fact that 6 plus 2 equals 2 plus 6 allows you to switch things around. And the sum of the a's is this one in summation notation, and the sum of the b's looks like this. That's effectively what I used here, except with a minus sign instead of a plus sign. But I could have put a minus sign there and minus signs at each of those spots, and I would have had a minus sign there. All right, does that help? Well, continue taking it step by step. When you look at these summations, what's the variable? Well, it looks like I've got 2 variables, I and n. But with respect to the summation, n is fixed. I is the variable. So, I is the thing that's varying from 1 to n. So with respect to the summations, I can factor out any constants like 50 or 125. I can also factor out any factors of n. In the end, n is going to be a variable that I let go to infinity. But as I do the calculation here, n is fixed. Some fixed positive integer like 17 or something. So any factor that involves n, like this division by n squared or n cubed, can be factored out. I can write the first summation is 50 over n squared times the summation I goes from 1 to n of I, and minus 125 over n cubed times the summation I goes from 1 to n of I squared. And this is progress because each of these summations turns out to have a formula. In fact, we saw the formula for the first one that I circled there last Friday. Mathematica, what is it? Mathematica is programmed to be able to figure that out. If I use one of the palettes, there's summation buttons, like there are integral buttons down at the bottom here. Okay, why is my mouse not working? There we go. Hit a summation button. Type it in like you see it. I tab over 1 tab n, putting those things in those boxes. I just use the tab key to go to each next one. What goes here is just an I. Mathematica says the answer is 1/2 times n plus 1. More typically, I write that as n times n plus 1 over 2 is the way I write that. Is it right? Yeah, it is right. And it's something actually worth knowing. You have to memorize it? No, but I would suggest memorizing it. It's worth knowing if you need to take more math classes. It does work. Like, for example, if n is 10, what's 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10? According to that formula, it should be 1/2 times 10 times 11. 55. And it is, that's right. If n is 11, it should be 1/2 times 11 times 12. 66. Yeah, 55 plus 11, 66. It's the sum of the first n positive integers. What about the sum of the first n perfect squares? That's what that is. Right? 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared, etc. That's 1 plus 4 plus 9 plus 16 plus 25 plus 36 plus 49, etc. What's the sum of those? That can be found as well. It's more complicated. N times n plus 1 times 2n plus 1 is all over 6 is how I would more typically write it. These formulas, how are they derived? Actually, you can use something called discrete calculus to derive them. Discrete calculus, that's calculus without limits. There is such a thing. I mentioned this last Friday. I actually made a video about a month and a half ago, sometime in March, where I showed how to derive these things. It was for a different class called numerical analysis. If you know them already, they can be proved using something called induction. You remember ever doing induction in your past? Maybe you had a high school teacher who taught you induction. These are common exercises to prove using induction, but the induction doesn't tell you where the formulas come from in the first place, like who figured them out. And again, this one does work. Like if you try adding up the first 5 perfect squares and try using the formula, how about that? We got 55 again. If you try using the formula, you get the same answer. N is 5 here. 5 times 6 times 2n plus 1 would be 11 over 6 is also 55. I just use that formula. Right there. So it is working. So we're going to just trust that those formulas are right. And if we trust that they are right, that allows us to continue simplifying. This first thing, after I multiply by 50 over n squared, becomes 50. I'm not even going to bother multiplying out the top. I mean, I could. I think I'll just leave it like that. Same thing with the next one. I'm not even going to bother. I could expand it, but I don't really need to. Because now what I do, and I could subtract these fractions by getting a common denominator of 6n cubed, but I don't need to. Because it's good enough just to look at this now and say, let's now let n go to infinity. Take a limit of this as n goes to infinity. And this can then be figured out using things we talked about way back in the first month of the course, first few weeks. Limits of rational functions. Usually we thought of x as the variable and it was a continuous variable instead of n being a discrete variable. But as far as this kind of limit goes, it doesn't really matter. These are rational functions of n where the degree of the top and the bottom, the numerator and denominator, are the same. They're both n squared with this one, and they're both n cubed with this one. So the limit, yes, it could be figured out with L'Hopital's rule, but we don't have to figure it out with that. The limit is the ratio of the coefficients of the highest powers. The n squareds in this one, the n cubes in this one. N squared has a coefficient of 50 in the top here and 2 in the bottom. Instead of an equal sign, let's put an arrow. 50 over 2. And in this one, n cubed has a coefficient of 125 times 2, 250 in the numerator, and 6 in the denominator. This difference is going to approach, not equal, but approach this difference, which is, get a common denominator of 6, is negative 100 over 6, or negative 50/3, as n goes to infinity. So if I haven't made any mistakes, that should be the value of the integral. The arrow means take a limit as n goes to infinity. I'm not saying this difference equals negative 50 over 3. I'm saying it approaches negative 50 over 3 as n gets larger and larger. It gets closer and closer to negative 50 over 3. So because the integral is that limit, that should be the answer. And thinking about the application, if you want to convert this to a decimal, that would be negative what? 16.6 repeating? About negative 16.7, whatever units are, if we're talking about the bug moving across the page, probably the distance units are centimeters or maybe even millimeters if it's a really tiny bug. Let's say it's centimeters. The units for the original function as a velocity would have been in centimeters per unit time, say centimeters per second, just to pick something. And then this would have been in centimeters. It ends about negative 16.7 centimeters to the left of where it started if rightward motion is positive. This is the displacement or change in position. Of course, I mentioned last week about how it would be very unlikely to have a bug travel with this exact velocity, right? Probably impossible. But these kinds of problems where we can find out exact answers are still useful, for one thing, because they help you understand the content better. And for another thing is they can still be used to approximate more realistic motion. Polynomials are useful, especially for approximation of, messy real world data that's got some ambiguity in it, or maybe some measurement error and doesn't follow some simple formula like this exactly, but maybe approximate. In fact, that numerical analysis course I talked about, we do exactly that kind of thing in it. We use polynomials to approximate data. Because polynomials are simple, that's why. And these kind of calculations, at least if we use the fundamental theorem of calculus, are simple. I mean, yeah, that's not easy here, but in the end, when we use the fundamental theorem of calculus, as we're about to, for polynomials, it's pretty simple. Antiderivatives or polynomials are pretty simple to figure out. Let's do that right now. Let's confirm the answer with the fundamental theorem of calculus. So what I was just doing there with the Riemann sums and the limits and the areas, that's section 5.2. Fundamental theorem of calculus is in section 5.3. Again, I think most of your homework is going to be on 5.2, but a little bit will be on 5.3 for Wednesday. I'm trying to evaluate the definite integral from 0 to 5 of 2t minus t squared. That was my velocity function. If I didn't make any mistakes in the previous paper, I already know the answer. It should be negative 50 over 3. Not obvious looking at that though, is it? This function I call little f of t, it was the velocity in centimeters per second. What the fundamental theorem of calculus says to do is to find an antiderivative of little f. Plug in 5 into that antiderivative and then subtract what you get when you plug in 0. Plug in the upper limit minus what you get when you plug in the lower limit. That's what the fundamental theorem of calculus says to do, which makes finding the integral very easy. You don't have to worry about limits. That happened with derivatives. It's happening with integrals. With derivatives, limits of difference quotients was the basis for derivatives. But then we had all these great rules that allowed us to differentiate many, many functions, including very complicated functions, without limits. Right? Think about that exam question from exam 2 with the derivative. It was very nasty. It was like, what? Tangent of secant of something plus blah, blah, blah. I don't know. It was a very complicated function. Imagine doing that with the limit definition of the derivative. No way. I wouldn't want to do it, though I know the answer because I can use the rules. Same kind of thing happens with integrals. They're defined using limits, but happy day, we can use the fundamental theorem of calculus quite often to avoid limits. The same thing will happen in calculus 2, later in calculus 2, the last month and a half of the course. You'll be talking more about infinite sums. They're called series, specifically something called Taylor series and geometric series and things like that. Those are infinite sums that are defined in terms of limits, because you can't literally add up infinitely many things, so you have to define them some other way. But there are sometimes tricks for evaluating those sums without limits. Same kind of theme comes up. In multivariable calculus, same theme comes up. In multivariable calculus, instead of doing single integrals, you do things called double integrals and triple integrals. I mean, there are quadruple integrals and quintuple integrals and hextuple integrals. Yes, there are actually, though people rarely do them. Usually the biggest one people do are triple integrals, and those are hard enough. They're defined in terms of limits. But guess what? You can evaluate them without limits. There are also things called line integrals and surface integrals. They're defined in terms of limits. But guess what? Happy day, you can evaluate them without limits. It's the same song and dance every time. And it's great. Good that we don't always have to do limits every day in calculus. But you should know that everything depends on limits. So where was I going? Oh, okay, we're going to evaluate this with the fundamental theorem of calculus. I need a capital F. Capital F is standard notation for an antiderivative of little f. I need to do that calculation where capital F is an antiderivative of little f, i.e. capital F prime of t always equals little f of t over the interval from 0 to 5. In other words, for all values of t in that interval. Notationally, we also sometimes write this like this. I'm putting t equals 0 to t equals 5 there. Sometimes we don't bother with the t's, we just put a 0 and a 5. So the problem now is to figure out an antiderivative. Well, that's pretty easy. Just guess. In this problem, one example of an antiderivative is t squared minus 1/3 t cubed, right? Guess. Educated guessing. What function is going to have a derivative equal to 2t? It's t squared. What function will have a derivative equal to t squared? 1/3 t cubed. Got a subtraction there, so there needs to be a subtraction there. Do I need a plus c? No, you don't have to have a plus c, because if there was a plus c, it would cancel upon subtraction, this subtraction. because the plus c would be in both terms. You don't want to use one c in one of these and another c in the other. It's the same c, and you might as well use c equals 0 because that's nice and simple. Plug in 5. Was this the exact same problem we did before? I'm not feeling like this is the exact same problem we did before, except we didn't do this before. Didn't we get negative 50 over 3 for an answer before? Maybe we did. I'm feeling like we did this exact same problem as last time with the FTC, at least. I'm putting the zeros in there to emphasize they should be in there, but sometimes because they're zeros, that you get 0. Yeah, in the end, we get 25 minus 125 over 3, getting a common denominator of 3. That's 75 over 3 minus 125 over 3. Yes, that's negative 50 over 3. Same answer as before. If you wanted to, you could also break apart this motion that the bug travels into 2 pieces. There's the time period where it travels to the right, that's the first 2 seconds. And then there's the time period where it travels to the left, that's from time 2 to time 5. And I can figure out the total displacement by adding 2 integrals. You can do this problem. It's more work, but you can do it. As the integral from 0 to 2 of 2t minus t squared plus the integral from 2 to 5 of 2t minus t squared. It's going to be more work, but it does have a benefit. The benefit is it will tell you, first of all, how far the bug goes to the right before the bug turns around and goes to the left. And also the total displacement as the bug is traveling just to the left. Antiderivative to use in both cases is the same, t squared minus 1/3 t cubed. This one gets evaluated from 0 to 2. This one gets evaluated from 2 to 5. This one's going to be positive. This one's going to be negative. From 2 to 0, you're going to get 2 squared minus 8/3 minus 0. With the other one, you're going to get 5 squared minus 125/3 minus 2 squared minus 8/3. Notice that if I wanted to, I could completely cancel these 2 things. Where I'm pointing? Because they're the same, 2 squared minus 8/3, 4 minus 8/3. And there's a 0, the final answer would be this thing, which would be the exact same thing we got up here. So we will get the exact same final answer. But I'm not going to cancel them. I'm going to figure out what they are. 4 minus 8/3 is 12/3 minus 8/3 is 4/3. So I'm going to get 4/3 plus, yes, this is 120, this is negative 50 over 3, same answer we got before, and we're subtracting this thing, which is 4/3. And so because we're subtracting it, again, the 4/3 cancel. But I also could figure out what negative 50 over 3 minus 4/3 is. It's negative 54 over 3. I wrote this as adding a negative. Of course, that's the same as subtracting. But what this is telling me is the bug travels 1.3 repeating units to the right first before it turns around and travels to the left by negative 54 over 3 is what? Negative 18. It goes to the right by 1.3 units first before going to the left by 18 units. The net result is to go to the left by 16.7 units. When you combine these, you get the negative 16.6 repeating. So what I just did was worthwhile for 2 reasons. One is it shows you can break up the motion into pieces and you can figure out how far you go in each piece and which direction. And secondly, to illustrate a more general property of integrals, that if you integrate a function over an interval, you can integrate it over a smaller interval first and then integrate it over whatever's left over. And that is sometimes useful. Integrate from 0 to 2 first, then integrate from 2 to 5. Sometimes integrals are just really hard to do. I'm going to write down one that's harder to do. It is possible, but it definitely is harder. What's the integral? Oh, from maybe 2 to 10. I'll go back to using Lx here. Ln of x dx. Careful. In the fundamental theorem of calculus, you got to use an antiderivative, not a derivative. So I do not differentiate ln of x. I don't use 1 over x somehow. I need an antiderivative. I need a function whose derivative is natural log of x. What kind of function has a derivative equal to natural log of x? Boy, that sounds hard if you think about it. Like, I don't know. I know the derivative of natural log of x is 1 over x, but what function has a derivative equal to natural log of x? The answer, through a bit of guessing, can be found. The answer still involves natural log of x. Well, not quite. Let's see what Mathematica says the answer is. We can do a pure indefinite integral in Mathematica, no limits of integration. Remember, in Mathematica, log is actually ln. The philosophy of the person who programmed Mathematica, Stephen Wolfram, who's a physicist, is, well, what other log would you use but the natural log? So we might as well just call it log, even though it's one more letter to write down. So it kind of betrays laziness. But like, what else would you use? That's the best logarithm to use. So that must be the natural logarithm. Mathematica is saying the answer is x times natural log of x minus x. Is that right? You can always check it. The derivative with respect to x of x times natural log of x minus x. Mathematica is, of course, writing it in the other order, but that's the way I would write it. I need the product rule. The derivative of x is 1. So there's the derivative of the left times the right, plus the left function times the derivative of the right. The derivative of natural log of x is 1 over x. The derivative of minus x is minus 1. This simplifies to plus 1, and look, they cancel. Yay. It all simplifies to natural log of x. At least when x is positive. So we're in the domain of natural log of x. That's, by the way, every time you do a problem involving logarithms, you should remind yourself that the natural log's domain is positive values. You gotta remember these things just by periodically reminding yourself, thinking about it once in a while. Then it'll come back to you faster on a test. Of course, maybe you've forgotten it, so you can't think about it. So maybe you need to look it up to remind yourself. So I guess I got to use this function as an antiderivative. Is this my capital F of x? Sure, that can work. So I could write x ln of x minus x evaluated from 2 to 10. Which will not be a nice number. It's going to involve irrational quantities. If I plug in 10, I get 10 ln of 10, which is not a nice number, minus 10. If I subtract what I get when I plug in 2, I subtract 2 times natural log of 2 minus 2. This can be simplified a little bit. You can Oh, you can, for example, if you want, you can use properties of logarithms. You can make that 10 a power of the 10 inside. I could write that. I could also do the same kind of thing with the 2. And then negative 10 minus negative 2 is negative 10 plus 2 is negative 8. I also could use another property of logs to combine those. By the way, 10 to the 10th power is 10 billion. 10 billion. Whoops. And so I could ultimately write the answer as ln of 5 billion minus 8. How about that? Ln of 5 billion minus 8. You would never know that ahead of time, right? Let's see if it's really right. Do a definite integral in Mathematica, put a 2 here, 10 here, log of x here. Okay, Mathematica did not combine the logarithms, but it could have. The a numerical, this looks like it must be a really big number, but it's not that big, actually. It's about 13.6. And yes, if you do log of 5 billion minus 8 and do a numerical approximation, it is this. Oh, I must have made a mistake. Where's my mistake? Where's my mistake? Checking up here first. Ten to the ninth is a billion, so 10 to the 10th would be 10 billion. That's ln of 2 squared. Oh, it's, I see my mistake. That's a 4 there, so this is a 4 here. It's ln of 2.5 billion. 2,500,000,000 minus 8. $2,500,000,000. Yep, same answer. That's wrong. This one's right. I mean, got a number in the billions, you would think the number's really big, but you're taking the natural log of it, so in the end, the answer is not that big. What would happen if we tried to do this with Riemann sums? I'm about to show you how to program Riemann sums into Mathematica. You may need this on at least one homework problem, but I'm about to show you. First, define the function. We're doing the log of x. Next, define a, and then define b. For this example, a is 2 and b is 10. I'm integrating from 2 to 10. The answer, by the way, is the area under the graph of the logarithm. From 2 to 10. Graphically, what's going on here is we've got a picture that looks like this. The logarithm graph looks like this. And as x goes from 2 to 10, it's something about like that. And we're trying to find this area. And we're seeing it's about 13.6. I'm again about to program the left and right hand sums into Mathematica. LHS, okay, yeah, let's do it this way. LHS of n for the summations, n is ultimately the variable, just like I wrote it by hand. Within the summation itself, I is the variable. Do a summation button over here on the palette. Again, you get the writing assistant by going to the palette's menu and going down to writing assistant. And under typesetting, it's this last tab here. You can find buttons like an integral button and a summation button. I goes from 0 to n minus 1. F of xi. What is xi? It's a plus I times delta x. But what is delta x? It's b minus a over n. And then that gets multiplied by delta x. B minus a over n. That's how to program a left-hand sum. For right-hand sum, I'm just going to copy and paste it. Copy, put your cursor to the right of the semicolon, paste. Semicolons suppress output, but you can also think of it as separating different lines of code. Do RHS instead of LHS, change the 0 to a 1 and change the n minus 1 to an n, and that'll do it. Let's also do a trapezoid sum. Trap of n is the average of left-hand sum and right-hand sum. Now, going to enter all this. I've got semicolons in there. That's fine. Just make sure your cursor is somewhere in the cell. Enter this with doing a shift return. You don't see any output, but it's in memory now. If I do one of these, for example, LHS for a particular value of 10, the answer is not going to look very nice because it's going to write out the summation completely symbolically. Yeah. So get a numerical approximation, do / capital N. There we go. If I want to do all the approximations at once for a particular value of n, I can, for example, put them inside a list separated by commas. I can put an RHS in here and also a trap. This will give me numerical approximations to these summations with n equal to 10 for all of them, the left-hand sum, the right-hand sum, and their average. And yes, 13.6184 is the average of these two numbers. Go to try. 12.9746 plus 14.2621. Well, up to rounding, there's a slight rounding error, although it's rounding to the same thing. And 13.6, the value of the trap, that's not too far from the right answer. 13.6396 is the correct answer to 4 decimal places. This one's not too far away. And if I do a bigger value of n, like n equals 100 instead of 10, I bet the trapezoid one's really close. 13.6393, when the right one was 16.6396. We're within 0.0003 of the answer. These summations are approximating the limit. Is it possible to do the limit by hand here? What's LHS of an arbitrary lowercase n here? I don't know. I'm kind of, no, what, Pockhammer? What's Pockhammer? Oh, it's just a function you've never heard of. Named after somebody whose last name is Pockhammer, I guess. It's called a special function, a non-elementary function. There are plenty of them. There are hundreds, if not thousands, of non-elementary functions out there. You just never heard of them before. A couple famous ones you may encounter are ERF, which stands for error function, and also another famous one is called the gamma function. Couple examples of non-elementary functions. Can Mathematica compute the limit of this as n goes to infinity? Possibly. Let me just copy and paste this in here. What's the limit of 8 log of 8 to the n times 1 over n to the n, Pockhammer of n over 4 comma n, all over n as n goes to infinity? I guess it's 13.6396. By the way, the percent sign refers to the preceding output, so that's a shortcut for numerically approximating that preceding output. Wow, it worked. But yeah, I don't think I could do this one without technology. Yeah, I know for sure I couldn't. I mean, now that I've learned about it a little bit, maybe I can look it up and see how it's done. What is Pockhammer, for example? The first step would be you looking it up on Mathematica itself. Mathematica, what is Pockhammer? Mathematica does tell you. Gives the Pockhammer symbol and well, that's not much information. Okay, here's what it is. It's a times a plus 1 times a plus 2 times a plus 3, etc., through a plus n minus 1, which is related to the gamma function. It's capital gamma of a plus n over capital gamma of a. But what is the gamma function? The gamma function is defined by an integral. Integrals are used to define lots of functions, actually, lots of functions you've never heard of. Later in physics, you also learn about something called elliptic functions. They're defined using integrals. There's an elliptic function of the first kind and an elliptic function of the second kind. Is that like Close Encounters of the Third Kind? You heard of that movie? It's an aliens movie from 45 years ago. It's pretty famous, actually. Steven Spielberg. Yeah, Steven Spielberg's his first couple movies are pretty famous. His first 3 or 4 are like Jaws, Close Encounters of the Third Kind, E.T., and then he also got involved in Raiders of the Lost Ark. So anyway, why did I bring that up? I forgot. Anyway, you can do investigations into these things if you want. But yes, you should be able to just effectively copy and paste what I do here and make adjustments. You'll have to change the value, change what the function is, change A and change B, but you can keep these as they are. They're programmed for a general F. And then just plug in your value of n and do // capital N to get numerical approximations.